Hi there. In this next series of lectures, we'll be looking at this interesting class of protocols called gossip protocols or epidemic protocols. But first, let's start from the problem statement and slightly far away from where we want to be. The problem that gossip is trying to solve is called the multicast problem. So what is multicast? Suppose you have a group of processes or a group of nodes. Again, each of these processes or each of these nodes is potentially a process at some host on the internet or connected to the network. And essentially, all we need is that these processes or nodes need to be able to talk with each other by being able to send and receive messages. So here I have a red node which has a particular piece of information. And I have other blue nodes in the group that want to receive this piece of information. For instance, these might be computers on the floor of the New York Stock Exchange. And this red computer might have, or this red node might have information about a latest stock trade, which it wants to get out to the other brokers on the floor. This is the multicast problem. Okay, so this is the problem where you want to get information out to other members in your group. And of course, here I'm showing only one multicast message. There might be multiple multicast messages going around at the same time, each of them from potentially a different sender. Now, multicast is as opposed to broadcast, where you have a piece of information that you want to send out to the entire network, where everyone, all the computers or all the nodes on the network want to receive that piece of information. That's broadcast. Multicast, on the other hand, is more restricted. It's only within a particular group of nodes or group of processes. So what are the requirements from a multicast protocol? Well, two of the most important requirements as far as cloud computing is concerned are fault tolerance and scalability. The nodes themselves may crash because processes, after all, are failure prone, as we know. The packets may be dropped by the underlying network. They might also be delayed by the underlying network. And so you want your multicast to be reliable and have all the non-faulty recipients receive the multicast in spite of these failures and delays that might happen in the underlying network. You also want your multicast protocol to be scalable and have an overhead per node that does not grow very quickly as the number of nodes grows into the thousands, maybe even much higher, into tens of thousands or hundreds of thousands. So the protocol that is executed at the individual nodes as well as the senders is what is known as the multicast protocol. The multicast protocol typically sits at the application level, meaning that it does not deal with the underlying network. But this is not a given, because oftentimes the application level multicast protocols also talk to the underlying network level techniques such as IP multicast. Again, IP multicast is what's available in the underlying network itself. Typically, this is implemented in routers and switches. It's not necessarily an attractive alternative because even though it's available, it may not be enabled in many of the routers and switches. And so most of the multicast protocols that are deployed out there today, even though some of them may leverage IP multicast where it's available, most of them today are application level, meaning that they involve processes talking with each other without really worrying about what's going on in the network underneath. So one of the simplest ways of doing multicast is a centralized approach. You have the sender, it has a list of recipients, it simply goes through these recipients in, say, a for or a while loop, and it sends each of these recipients either a UDP or a TCP packet that contains the information, the multicast message itself. UDP stands for User Datagram Protocol. It is a connectionless and unreliable way of transmitting messages, but it's cheap and it's low overhead. TCP is Transmission Control Protocol, which is a connection-oriented way and a more reliable way of sending messages. You could choose either one of these. This is, of course, the simplest implementation. Now, one of the problems with this implementation is when it comes to fault tolerance. If the sender fails when it's halfway through its for loop, essentially only half the receivers would have received the multicast. Also, the overhead on the sender is very high. Imagine a group where you have thousands of nodes in the group, and in that particular case, the sender has to go through has to send a lot of messages, and this also increases the latency. The average time for a receiver to receive a multicast could be as high as order n, which is linear in the size of the group itself. So to address that, tree-based multicast protocols have been developed. Essentially, all of these protocols develop a spanning tree among the nodes or the processes in the group. These include network level protocols such as IP multicast, where the spanning tree is among the routers and switches in the underlying network, but also application level multicast protocols such as SRM, RMTP, TRAM, TMTP, and a whole bunch of others. First of all, this is attractive because if you build the tree well enough, if it is, say, a balanced tree, then with n nodes in your group, the height of the tree is order log n, and this means that the latency for a message to reach any of the nodes in the group is order log n, as opposed to centralized, where the latency might have been as high as order n. Also, the overhead on each member in the group, both the sender as well as any of the receivers, is constant, especially if the number of children is constant. Essentially, you receive one copy of the multicast message and you send out as many copies as you have children. However, one of the problems here is that you need to set up and maintain the tree. When node failures happen, the nodes in the system might actually not receive multicasts for a while. For instance, if this node at the leaf fails, then that's the only node that's affected. When that node rejoins the tree, it will start to receive multicasts. However, if this node that's closer to the root fails, then essentially you have a situation where none of its descendants will receive any of the multicasts that are sent before this part of the tree is repaired. Perhaps it is replaced by another node, or it recovers and rejoins the tree at that particular position. So because, as you know, failures are the norm rather than the exception, you're always going to have situations where nodes are failing all the time, and you have to spend some amount of bandwidth and resources in continuously repairing the tree all the time. So a little bit more on the tree-based multicast protocols. Essentially, these build a spanning tree among the processes of the multicast group. They use a spanning tree to disseminate the multicasts. They might prefer IP multicast where it's available to do this initial dissemination. Thereafter, they use either acknowledgements, positive acknowledgements, or negative acknowledgements to repair the multicasts that are not received by the receivers. Positive acknowledgements are often called as ACKs, and negative acknowledgements are called as NACKs. For instance, the Scalable Reliable Multicast Protocol, the SRM, uses NACKs. Essentially, when a receiver has not received multicast messages that it is expecting or for a while, it sends a repair request up towards the root of the tree. And when these repair requests are received, nodes closer to the root of the tree send the latest multicasts that they have, or the missing multicasts as far as the receiver is concerned. One of the issues with tree-based protocols is that the ACKs and NACKs might implode, meaning that there might be very large numbers of ACKs and NACKs. For instance, for multicasts where the initial dissemination was not very successful and was received at very few nodes in the group. To avoid this, the SRM protocol adds random delays at the receiver. So receivers, when they realize they need to send out a NACK, they don't send out the NACK immediately. They wait for a little bit of time and then they send it out. If they need to send a NACK multiple times, then they might use an exponential backoff, meaning that they wait for a period of time that doubles every time they wait. Also, the messages that are sent out might also be subject to exponential backoff. The RMTP, the Reliable Multicast Transport Protocol, is similar, but it's slightly different. Instead of using negative acknowledgements, it uses positive acknowledgements. So the receivers periodically send a digest or a collection of acknowledgements for all the multicasts that they have received so far. And if any of the messages are missing from these ACKs, then those messages are sent downwards towards the receivers. Now, once again, you can have ACK storms here, and to avoid these ACK storms, there are certain receivers marked as designated receivers, and the ACKs are sent only to these designated receivers, and then these designated receivers forward the corresponding multicast messages down the tree. However, there have been studies that have analyzed the scalability of these protocols, and even in spite of the random delays and the exponential backoff, both these types of protocols, both NACK-based and ACK-based protocols, still suffer from a large number of NACKs and ACKs that are sent out, and the number of these NACKs and ACKs typically grows linearly with the size of the group itself. So these protocols are not as scalable as they were intended to be. So this motivates the development or the introduction of our gossip-based or epidemic-based protocol.